Hello and welcome back. This is the second video on section 2.3, and this will be a short video on some common ways that graphs can be built to deceive people. So the reason that we're explaining this is so that you guys won't be deceived in the future, and that the graphs that you make will be hopefully a little bit less deceiving than the one that I'll show you. So one typical way that graphs can be built to sort of deceive, so like hiding some information, is when graphs are built with a non-zero vertical axis. So for instance, maybe we're playing a game and we record how many points we score in each game. So game 1, game 2, game 3, and we see this and we go, oh, game 3 I scored barely any points compared to game 1 and game 2. This looks like it's about 1/6 of the height as game 1. But then we come over here and we look at the axis, and we see that our graph starts at 15, and up here is 30. So maybe a better graph would be one that would start at 0 and wouldn't hide this information. So if I call this 30, say 20, and 10, and we had game 1, game 2, and game 3, game 1 was at about 30. Game 2 was at 25, which would be halfway between 30 and 25. And then game 3 we scored a little bit over 15, so it's a little bit over halfway. And when we look at this graph, yeah, game 3 we scored a little bit over half of game 1's points. But this does not look like half. So these graphs contain the same information. And it's important to recognize that here, this graph is not necessarily incorrect. It's just been displayed in such a way that if you were going to look at this graph for 2 seconds and move on with your life, you would assume that game 3 had a lot lower score than it did in reality. So one of the reasons why we really want to be aware of this is when you look at a graph, but you're not going to spend a long time looking at it, it's important to know what the graph should indicate. And for instance, a bar graph or a histogram, so these would both be bar charts. What's important here is the relative heights here, the relative proportions of the frequencies. So in the first one, it looks like game 3 is less than 1/6 the points of game 1, but we can't see that unless we're on a scale that starts with 0. If we're on a scale that goes from 15 to 30, then things get a little bit more obscured. Now, there are other ways of obscuring information as well. Here, we just started at a number that's not 0. You can also see graphs where the labels along the side don't go up linearly. So the space between the first and second, say, tick marks is going to be longer than the say the third and fourth ones. These graphs, again, there may be reasons why you'd want to construct a graph like this, but at a glance, it will be hard to see what those numbers are. And then the last thing in this video that I'll mention are pictographs, meaning that they use pictures to represent data. And the problem with pictures is that you have to communicate clearly what information about the pictures is representing the data. So for instance, maybe we see that school A gets a little bit less money than school B in some grant, and we draw a couple of squares to represent that. This square, compared to the bigger square, is certainly smaller, but the question is how much smaller. The side length here looks to be about half the length of the side length of this square. So does school A get half of the money that school B did? Or are we looking at area? When we look at this square, if the side lengths are exactly half of this square, that would mean I could fit 4 of the smaller square into the bigger one. So did school A get 1/4 of the money that school B did, or did school A get 1/2 of the money that school B did? This gets even worse when you represent not only two-dimensional pictures but three-dimensional pictures. So instead of a square, we've got something like a cube. So now the question would be, is it the side length? Is that representing how much, or the difference of money? Is it the area on one face of the cube, or is it the volume of the cube? And if you think about this carefully, the volume of school A would be 1/8 the volume of school B. So it's nice, sort of as a picture, you can easily recognize that school A got less money than school B did, but can you assign a numerical value? Is it half, a quarter? If it's volume, is it 1/8 less? And this is where things become a lot less clear. And in particular, if you only have two data points, you might as well just list the numbers to compare them, and there's no need for pictographs or a chart. And in fact, up to say 10 values or maybe a few more, maybe it's just easier to list the values explicitly than using a graph. So there are times and places for certain types of graphs, and to avoid certain pitfalls like using pictures and, for instance, using non-zero axes. So this is just something to be aware of when you are creating graphs and when you are reading other graphs.